Sorry, I'm just getting used to the clicker. So is this a clicker, I think? Yes, cool, okay. Hi, today, as I was introduced, I'm going to be actually bagging AWS a little bit. Really, this point of this talk is to kind of go into maybe some of the patterns that cloud providers recommend, but aren't necessarily best for the customer. Sorry. Cool. So yeah, a bit of introduction about myself. Already gone through it, but yeah, senior platform engineer is the first mode. Recently started moving into, I guess, the data engineering space. AWS IoT hero. That doesn't mean I'm not going to bag AWS though. And I'm a lover of cats. I can have anywhere between 3 and 20 cats at any given point in time. So I guess what's the plan of this talk? We're going to mainly focus on data ingestion strategies for IoT systems. We're going to focus primarily on S3 as our destination. I will go into a little bit more later, but it's mostly due to its cost efficiency and the ability to get data into raw form. We're going to dive into Apache Iceberg as our engine for accessing that data, and then build a data pipeline around that for showing you how you can get data into Iceberg. And then finally, some access patterns for users and your data teams. So I'm going to talk briefly about some typical IoT patterns. I'm aware that this is not an IoT conference. This is a data conference. So just put simply, there's typically 2 different patterns you'll see. If you're working with IoT sensors, you'll have sensors that communicate directly to the cloud. You'll have one or many of those. There won't be anything like offline. It'll be purely just talking to the cloud. So an example of this might be an air conditioner in your house might talk to the cloud, communicate information, and you may be able to actuate that air conditioner from a thing like an app. The second pattern is one that involves an edge. This is probably a pattern you'll see a lot in WA because we have a lot of mine sites that are, don't have the best comms. They need offline capability. They might want to do decisions at the edge. I guess the important thing to note is that there's 2 big patterns, but you can have a mix of both. Like you might have some data go straight to cloud, some data go to the edge, some data get buffered at the edge. I guess there's a real mix, and that's good. So I guess a few caveats about this talk is that I'm focusing purely on the bulk data ingestion piece. So I'm not dealing with safety critical systems. I'm not dealing with systems that need to be actuated, so sending data back to the sensor to tell it what to do. This is just one piece of the pie. You need to think about all 3 of those strategies when you're dealing with IoT systems. I'm going to talk a little bit about Greengrass. Now, Greengrass is like AWS's edge IoT platform. However, none of the things I talk about in this talk can only be done on AWS. Like the idea is that this is just a pattern. You can replicate it to any cloud. You can replicate it that's on-prem for all that matters. And I think the final thing is that it's also the way the data lands is also very agnostic. So when I look at some of the kind of existing patterns for ingesting data into the cloud, I guess the lowest common denominator is that data usually lands in S3. If you're using something like Kinesis or Firehose, they're the AWS versions of getting data up. Eventually, data is probably going to land in an S3 bucket. So if you're doing real-time analytics on data as it comes in, you're probably going to store that data long-term to do further analytics down the track. That's probably going to go into S3. If you're doing edge decision-making, there's a very good chance that you're going to want to store that data as well, so that if one of the decisions was wrong, you're able to go back and check that data. Typically, even if that does pipe through another analytics system, most of the time, data is going to probably be stored in S3, at least under the hood, depending on your database engine. And thirdly is uncertainty. Like if you don't even know what you're doing, you're a team that's sort of been stood up and given a lot of money to do something. You hope you can produce something, but later down the track in 6 months, when the team asks you what you've been doing, you can point to something and say, oh yeah, the data's right there. So I guess given the prevalence of S3 across these sort of cases, I really wanted to focus on that and see what we come up with. I guess the question I get a lot is, okay, S3 is pretty expensive, right though? I sort of retort with, I think you're doing it wrong when people say that. If you're just raw uploading data to S3 with no consideration of what you're doing, yeah, you're going to spend a lot of money, and I'll go into that in a sec. I've got some graphs. I guess the trick is you need to be batching data. You need to be getting into a format that's going to be accessible to your databases earlier on rather than later. So like I said, there was going to be a graph. This is fairly unrealistic, but I've got the comparison of S3 if you're going to upload one piece of data to the cloud. It's going to cost you what was it, like 50 grand a month, like for effectively 4,000 messages a second. It's like ludicrously expensive. You wouldn't do this. I'm sure there are people who do this, and it makes no sense. The second most expensive option is probably MQTT. MQTT is like what I was talking about to start with, where you've got a device connected directly to the cloud. Most of the time, you won't do bulk upload of data using that. You only do what's necessary. I think a problem is you typically will get directed towards that a lot of the time. So you might end up having a case where your team stands up a system that's pumping data to AWS via MQTT, and then you start pumping more data, and then all of a sudden you're spending a lot of money. So I guess the reason why the S3 cost is so high, though, is because you're charged based on API calls. So S3 put object, 1 or 2 is not going to cost you much, but thousands and thousands and millions a month is going to cost you a lot of money. So I've removed kind of the outliers, the stuff that doesn't make any sense. We're really going to focus on, I guess, the kinesis options and batching data with S3. So when I say batching, what I mean is bundling up 40, 50, 100 records into a gzip file and then uploading it directly to S3. What we're actually doing under the hood is very similar to kinesis data streams. I guess Firehose is also another really good option for this. However, Firehose they bill on a model of 5 kilobyte increments, which it seems reasonable, but you do need to sort of kind of batch your data together into 5 kilobyte amounts if you want to get the most for your money. So whereas Kinesis data streams is probably, I'd say it still is probably the best solution for a lot of customers. I know I'm saying this, I'm trying to sell a different solution, but I think if you're getting started, Kinesis data streams is probably where you're going to land because it's probably the most managed solution. It is, however, kind of hard to use. I'll talk about that in a sec, but I guess some of the cost findings was MQT, good solution, probably ludicrously expensive if you're doing batch bulk uploads though. Firehose is a decent solution and one that you might use, but you need to be aware of the 5 kilobyte minimum. And then Fire or Kinesis data streams, good option, fairly difficult to use. So the libraries available to interact with it are only available in Java. You can use, like, Greengrass has a module that allows you to pipe data through it, but again, you need to be using Greengrass for that. So it's a bit of an investment to get it yourself up and running. And then finally, I guess S3 is what I'm trying to really shill here. I like it because it's cloud agnostic in the sense that, like, every cloud has a blob store. Like, no matter what you do, you're probably going to have a service that offers storage like that. It also can be the cheapest option if you're batching. So let's go through, I guess, the proposed design for the edge. Again, it's Greengrass specific, but the actual pattern itself can be broken down into a few different steps. The goal of this solution is really just to batch data up into gzip files and upload to S3. It also handles offline capabilities, so if your data goes offline, it keeps batching and buffering on disk, keeps getting put into batches, and then when the internet comes back online, it all gets uploaded. So the first part of this solution is, data gets put in. We use a sub-service of Greengrass called StreamManager. Nothing super crazy about this. It's really just a topic-based system for pumping large amounts of data into the cloud. StreamManager is nice, that's why I used it. You don't necessarily need to use it, but we're using it here because it allows us to just push data to a topic. The data is read on the edge, it's bundled into a gzip file. Then when the file lands on the disk, we use another feature, or another component, part of my component that I've written is, it sees that file has landed, so the gzip file lands. It publishes a message using a kind of advanced feature of StreamManager called export tasks, which is a way to get StreamManager to upload data to S3 for you. The nice thing about StreamManager export tasks is that it supports partitioning, so you can actually pre-partition your data. So when it does the upload, it will put it into like a Java string style timestamp, which is really handy, and you'll see in a second because it allows us to query really easily from like a Hive format. And then finally, you also get a response back from StreamManager when the file's been finished uploading, so it handles things like retries, multi-part uploads, everything like that. We just delete the file from disk when it's been uploaded. Like, you could maintain it if you wanted to, but again, this is just an example. You don't necessarily need to use my solution. It's designed as like you could write something bespoke yourself. So your data is landed in S3. So how do you query it? We're going to be using Athena to query it, just as an example. But as you can see, the data's in a Hive partition format. So I know data engineers in the room probably look at it and say, cool, look, I can probably immediately start using it, and you can. So again, we're using Athena. I know the schema, so I'm adding it to my create table. I'm using a feature of Athena called partition projection, which allows you to not have to rebuild reprocess the table whenever a partition changes. So you just define what the partition format is of your S3 bucket, and there's no need to do any side maintenance to get it to pick that up. I think you have to do like a MKSG repair on something on the table if you don't have this. So really handy little feature. We set the table format to gzip because that's the data that our format, or what our format of data is in. If you're using CSV under the hood, you use the CSV equivalent. If you have CSV gzip, you know what I mean. I guess another bonus, there's an example of me querying the data. Again, we get the partitioning built in, so straight off the bat, your data's landed. You haven't really done anything else. You just start querying it. I thought this was quite cool. Like, I'm fairly new to the data space, and I guess when I saw this for the first time, I'm like, wow, this is actually pretty powerful. I feel like this is fairly flexible. The only problem is, like, what if I don't know the schema? So that's where, like, I guess this little bonus comes in. You can use the Serde regex property to basically say, hey, I just want to capture everything in the column and put it under a column called like JSON string. Again, using partition projection, we can then like query the entire string. And like, maybe you don't talk to people in the business, maybe you're a data team who's not really engaging with the IT team, but you still need to be able to understand like when pipelines are failing. Maybe you don't have a data contract. You can at least see the data that's landing and be able to, like, I guess, retroactively maybe fix the tables. So again, I've kind of ignored the elephant in the room, and that is that if the device goes offline when it's uploading data, the partition is going to be wrong because the export task doesn't take into account, it only takes into account when the file's uploaded to S3. And I guess that's where, Iceberg comes in. So Iceberg solves a problem for us, which is that we don't want to be running external jobs like Glue to rejig partitions and put data where it needs to land. Iceberg is fairly new. It only came out like 3 or 4 years ago now. We're going to be looking at it as a solution to a few different problems, which is partitioning, schema evolution, and dealing with, I guess, speed and a more consistent experience. So to start with, we'll talk about partition evolution. So say that you ingest your data, and when you did it, you set it on a day. You have your partition set to a day. A few months roll around, and now you want to do it per hour. I guess traditionally, you would probably need to reprocess your data, put it into the correct partitions in the bucket in order to achieve that. With Iceberg, it's sort of handled for you under the hood, completely seamless to the user as well. So you change the partition, and the user still queries it in exactly the same way. It's just that the metadata and the way that Iceberg works under the hood processes where and how queries need to be executed and planned based on the changes you made to the partition. So for me, this is like fairly important because we didn't really know what we're doing to start with. We're pretty sure we know how we're partitioning our data. We think this is right. But in 2 months' time, it's going to change. If we don't have people who are able to do this full time, we wanted to pick a solution that allowed us to move fast and change things without needing to do a lot of kind of work to fix things. I guess the other thing is this is fairly invisible to the user. It's all transactional. So while we're making changes to, standard Hive style table partition changes, there's a good chance you're going to have an outage. You might have some queries fail. I guess the way that Iceberg works is, it's either one way or the other. It's all done in one transaction. So when you change the partition, there's not going to be an outage for your user. Schema revolution is another really big part. Probably the reason a lot of people would pick Iceberg, actually, because you can add, drop, rename, update, and reorder columns. This is all done because the columns aren't based on names. They're based on IDs under the names. So it solves a big problem people might have where if you drop a column and then in a year's time you bring a column back and then suddenly data comes back, because it's called zombie data. Because it's all based on these IDs, you don't have that case where a reused column name is going to bring back old data. This, again, all transactional based. So if you're making a change as you go, users aren't going to get half their data correct, half the data not correct. If they're running a query, they're not going to be getting lying data. Another really handy part of Iceberg is it supports time travel. So every time you make a commit or insert into Iceberg, it creates a new snapshot I'll talk a little bit later on the, I guess, the side effects of that, but it's really handy because it means that you can query data at a point in time. So if you change partitions, or if part of your business is not really ready to move to a new version of a table, they can just say full version and then read it either as the snapshot ID, or you can even use named snapshots, I'm pretty sure. And it allows you to query data at a point in time with schema and petition. So if your petitions have changed as well, you can query at a different time. And I guess finally, I thought this was quite interesting when I was doing some research into how Hive to Iceberg would look like. What I saw is the costs are quite significant, because when you query from Hive, you're paying a lot just to list directories. So when you're trying to query data, it's going through all these different partitions, trying to find the files it needs. With Iceberg, it's all metadata driven, so you have a metadata file that tells, I guess, the planner where to look for exactly the file it needs when it's actually performing queries. So you end up with a really stable, static cost, I find, because it's always going to execute in the same way, and you're not doing kind of needless reads on objects that aren't needed. So another really handy thing that Iceberg supports is you can specify the file size and bytes that you want data to be compacted into. So if you're putting data into a Hive partition S3 bucket, for example, and it's not optimized size, so say usually you'd use Glue for compactions, you'd come through a few months later, go through the entire partition of the bucket and just compact all the data into one file. That kind of cuts down the cost of the S3 get objects as well. Iceberg handles this for you by just compacting it all based on the file size you want. So in this case, I think an example in a sec, I'll show you what I mean. So in terms of cost, I used an example here where it was 100 records, 16 kilobytes. It's not really ideal. You're uploading a 16 kilobyte gzip file to an S3 bucket. It's probably not what you're going to do, but if you did, scaled out over time, you're probably looking at about double the cost. I've set my Iceberg table here to 512 megabytes, which means that the file will just keep compacting until there's 512 megabytes, and that's how I'll store it. So whenever you're making a quest, you're going to be requesting 512 megabytes within the file. So the second, this is probably a more realistic. This is if you were doing, glue jobs to do compaction. And what I found is the price is comparative, but what it doesn't take into account is the fact that you need engineering time. You need engineers to run these glue jobs. There's going to be outages when you're doing compactions. This is all stuff that you need to plan for. So I guess it's comparative, but that it doesn't take into account engineering. So now let's talk about how we're going to get data into Iceberg. This diagram I was told was fairly complicated when I threw it on the screen, so I put a goose there to, I guess, calm people down. Don't be intimidated. I'm going to dive a little bit more into it. It looks complicated, but as you see in a sec, I can break it down. So I guess the goal here is we want to get our data that's stored raw in S3 into Iceberg. And how do we do that with as minimal cost as possible? So we're going to use a feature of S3, which is called object events, which basically means when an object gets created or it lands in our bucket, it fires an event. We're going to take that event and we're going to put it into SQS. SQS is just a queuing system on AWS, and we're going to use the information in that SQS event to follow through. So you can see some data that's available in the actual event. It's just the file path and the bucket that it came from. Our goal here is to pipe it to a Lambda function. We'll do something in a sec. So we're going to do batching. So we can take more than one of these sort of already batched files and batch them further if we wanted to. It depends on when you want data to be available. Because obviously if you wait for 5 or 6 different gzips to come in before you do a batch, you're going to be waiting for more time before data is going to become available to users. This is all pre-configured. This is all configurable if you want to. The goal here is that we're going to copy some of the data from landing to a scratch bucket that's set to basically delete data after 7 days. The idea being that once data is ingested, we'll still have the raw landed data, but the scratch data is not important because it'll be in Iceberg. So then we create our Iceberg table. Usually you wouldn't do this as part of the Lambda. I've just put it in here because ease of use, but you're going to want to create an Iceberg table. All you really need to do is you specify the table property as Iceberg. This is all done through Athena and Glue. This might be kind of different depending on what cloud provider you use, but I'm pretty sure most cloud providers offer Iceberg now. It's definitely new, but it's not that new. So when you look at this, you probably say, wait, why are you specifying the table format as Parquet when our source data is JSON gzip? Well, that's for this next step. we create a temporary Hive-style standard table that points to that Scratch bucket where all of our Scratch data is. We tell it the source format we're in, so we're in JSON gzip. This is, I guess, the great thing about this pattern is at this stage you could switch that for whatever your source data is. So if you're using CSV, gzip, whatever you wanted, Parquet, you're just going to put it into here as your temp table, because the idea is temp table is created, and then the temp table is copied from into Iceberg. So this allows you to, I guess, fairly cheaply get data into Iceberg. We'll talk about cost a little bit in a sec. Another great advantage of this is, I guess, it's all. If something fails, you're going to get a message go back to the dead letter queue, which is just a way to reprocess events. All of this can be reprocessed sort of idempotently. Nothing you've done has actually really written, even if it partially writes data to the database, when you rewrite the event, you're going to just write over the top of that data. So from the perspective of, I guess, repeatability, like it's been really nice. Like I've been able to go to sleep. Teams have been able to upload data, and then like I wake up in the morning, and if there's any failures, I can go check the dead letter queue. I can see what the failures are. I can, work out why they failed, and then reprocess all the information. And then like the bars where there's missing data will just like refill. It's really nice to watch. So Iceberg, there are some problems in that you need to deal with table maintenance. Every single time you commit data to the Iceberg table, a new version is created. New version means more metadata. In a lot of cases, you'll find metadata can be more, can take up more space than the actual data you're storing if you don't handle it appropriately. So in this example, like we've got 450,000 versions of the table. You can disable automatic versioning on Glue with an option. This will be different depending on what your provider of Iceberg is. Schema changes are still kind of hard. There's not really any tooling around it right now. Like traditionally, you might use, I don't know, a Limbic or a Fire. I'm not sure what you'd use, but none of that tooling is available for Iceberg. It's all very, you need to use the SDK. It's only available in Java. There's like a Python version, but it's not really complete. So just forewarning. The Athena Iceberg has some odd behavior, really odd behavior. Like you can't use equals characters, but it's not documented. So in the file pathing, in Glue, they label something milliseconds, but the API returns seconds. And when we reported this to AWS, they said it'll change the documentation. And I was like, this isn't a documentation problem? And they were like, Anyway. The other thing is, if you delete a column from Athena, it'll still show up. Sorry, if you delete a column, it'll still show up in Glue and Athena. And the service team said that there was a rationale for that, and it's to do with lake formation, but we're not using lake formation, so it's really complicated for us and confusing. And then they closed the ticket, so that was that. So there's some quirks, but I won't say it didn't make us not want to use Iceberg. It was just, this is stuff that I guess AWS needs to improve, and they are working on it. Like to their credit, they are working on this. They take all our queries very seriously. So finally, how do you visualize this data? We just used Manager Grafana because it's got an Athena plugin. We slap it in there, and we can just start querying data. The queries can all be viewed behind the scenes in the Athena kind of recent queries console. It gives you an idea of like how much data you're querying and how long they take. We found that like most queries take about 1.5 seconds, which is maybe slow if you're using like a time series database for IoT data normally, but when you think about that as that's like consistent 1.5 seconds, no matter how many panels, no matter how many queries you're doing, you're always going to get a really consistent result for your queries. Like it's fairly good. Again, that's my full database, just some random data I threw up there. It was fairly easy for me to set up though. All the source code for this is available on my GitHub. Come see me after if you don't get a link, but this includes all the IoT stuff. There's like a CloudFormation stack for the full kind of Iceberg setup. I've got the QR code in the next slide as well when I talk through it a bit more. So I guess what does it cost? That's probably what most people are thinking. So we'll use an example of like 10 terabytes. If you wanted to query 10 terabytes through Athena, you've got about 16 kilobytes per file, and your Iceberg file size is configured to 512 megabytes. So you'd be looking at about $3 monthly for the put objects uploading, about 1 cent for the get objects, and that's because of the compacted nature of those files. The actual data queried is about probably $27, $30 I found. I guess it's going to depend on like, you probably aren't going to, there's going to be other costs. This is all very hypothetical, but it gives you an idea of like, so $230 monthly for the S3 storage. That's probably not going to change. Even if you're using standard Hive, that's going to be probably identical. Athena costs about $50 because it's $5 to a terabyte to query. And I guess this is not taking into account the compression ratio because I started to write the calculations for that, and I sort of just gave up because I realized it's not really the point. You just know that that cost is going to be a lot cheaper than what's standard, but it's going to be, that would still be just as cheap if you're using Hive as well. Something not pictured here though is the KMS costs. If you're using this at a business, you should be using KMS or some kind of encryption. KMS is definitely going to be your most expensive, I guess, part of this. Like, you need to take into account the fact you're going to be dealing with decryption events. So whatever the price is here, you're probably going to have to double it because that's what your KMS cost is going to be. So the cons of the whole of this is that it's not fully managed. Like, Iceberg is kind of 90% managed. You need to deal with the table maintenance yourself. In the GitHub repo I showed, I do have like a state machine that will deal with the maintenance for you, but your business case is going to be totally different. You might need snapshots that last like a year and things like that. So it's also very SQL-y. If you're not used to SQL, you're going to hate it. It doesn't have much tooling, which I already mentioned. And it's also kind of not battle hardened. It's new, very, very new in, if people are using Athena, not many people are using Iceberg, I've found. And even talking to the service teams, I get the impression that not many people have touched it at all. So I think we're a little bit early to the party, but we're still able to use it in production. The pros though, the price can make a lot of sense. Since all prices are usage-based, you're not going to have like a weird billing where you accidentally leave like a glue DPU interface or something running, and suddenly you've got like a $300 bill, and you're like, what the hell happened? Like, everything is usage-based. So like, unless your teams are uploading more data, you're not going to be spending much more money. You've also got data in a raw format, so it makes sense. So if you don't like Iceberg in 6 months' time, you can just revert back to what you had before, which I think is kind of cool. It means your team could transition to Iceberg just to test it out. And again, resilient and flexible in terms of you've got events that are triggered based on S3 events. And if anything fails, you just go back, redrive those messages. So that's, I guess, me. Thanks.